Welcome to Practical Power Electronics, video number 4. In this video we will compare the 3 different current measurement methods used in power electronics. A fast shunt, Rogowski coil and current transformer. Before we start the actual measurement, let's briefly go through the basic principles behind each of these methods. All the 3 sensors measure the same current, but they are based on very different physical principles, and that directly affects bandwidth, accuracy and usability. Fast shunt is resistive element. It converts current directly to voltage using Ohm's law. Which means V is equal to E times R. Because it measures current directly, it works from DC up to very high frequencies. However, the shunt is galvanically connected to the circuit, and its geometry strongly affects its dynamic behavior. And this is basic shunt, but when we want higher bandwidths, we are using shunt like this. This is called coaxial shunt. It means that parasitic inductance is removed or minimized. And this means that the current flow from here, this is cylindrical shunt element, goes up here and go back here. So when current goes here and here, they cancel parasitic inductance away. In this setup I don't have a coaxial shunt, but I have a shunt for which higher bandwidth is tens of megahertz. And Rogowski coil measures. It's a coil around a wire, and current inside the wire, if current changes, it changes magnetic flux around the wire, and this coil picks up this magnetic flux and creates small voltage which is proportional to dI/dt, which means it's react change of current. It cannot measure direct current, it can measure only changing current. Rogowski coil is an air-cored coil placed around the conductor. It does not measure current directly, but the rate of change of current. the output voltage is proportional to dIdt, so the signal must be integrated to obtain the actual current waveform, and this over here is an integrator, basic op-amp circuit. This capacitor and these resistors, and op-amp, this is integrator. We have to add this resistor, otherwise it integrates small offset errors and drifts plus or minus rail. But at the same time, this resistor here dictates lower cutoff frequency. Okay. Next, current transformer. The current transformer, or CT, is a magnetic core-based sensor. Like Rogowski coil, it only measures chasing current. Not DC. Compared to Rogowski coil, CT usually have better low frequency performance and higher sensitivity, but their bandwidth and linearity are limited by the magnetic core. This is the magnetic core. I have better picture here. This is magnetic core. It could be iron or higher frequencies can be used ferrite core. It's a basically transformer. Primary turns is 1 and secondary turns could be something like 50 or 100 or something. It's up to application. And secondary winding is not short circuit, but close to short circuit. It has could be, for example, tens of ohms resistance. Okay. In this video, all three sensors measure the same current under identical conditions. This allows us to directly compare the step response, bandwidth and practical limitations. And test setup I will use is this one. I have current pulse generator guided by function generator, and this is a current loop. I can create 20 amps current pulse with sharp edges. Shunt, the CT and the Rogowski coil and oscilloscope. Okay, let's move to the actual measurement setup. Here we can see the test setup. Current pulse generator, fast shunt, Rogowski coil and current transformer. And over here, function generator, which creates control voltage. This is the oscilloscope screen. Here we have control voltage, and this one yellow line is current measured by fast shunt. it is 5 amps per div, 5, 10, 15, little bit less than 20 amps. If we look the rising edge, let's put a little bit more speed. Something like that. We can see over here it's about, rise time is about 100 nanoseconds, and this is curve that the Shunt give us. Now we add Rogowski coil. We can see Rogowski coil, the rise time is about the same, 100 nanoseconds, but it doesn't have small oscillation like the Shunt has. It's smoother, and we can see very small, maybe 10 nanosecond delay compared to Shunt response. And we can add current transformer. Now we see green line is current transformer. It has little bit more oscillation, but it's a little bit sharper and very tiny delay, smaller than Rogowski coil. At this speed, this speed of rise time, they look quite similar. Let's change a little bit, go slower. Now it's 50 microseconds per div, and this is 100 microseconds. We can see over here that yellow line, which is the Shunt, it's quite flat, and blue line, it's decays. It has droop. And green line has also droop, but not so much as Rogowski coil. If we increase the pulse length, we can see more clearly this droop. Rogowski coil have highest droop, and second is current transformer, and fast Shunt is flat, no droop at all. We can copy this screen. Like this one. And they copy also this one. Okay. Now the measurement is done. Here we can see the test results. This is rise time of Rogowski coil, blue line, and yellow is fast shunt and green is current transformer. We can here read rise time is about 100 nanoseconds each. And we can estimate upper cutoff frequency based on that. Upper cutoff frequency is 0.35 divided by rise time, which is 100 nanosecond, which is 3.5 megahertz. But Rogowski coil is commercial device and it has 50 megahertz bandwidth, which means that this rise time is not because of measuring sensor, it's because of current pulse generator. So current pulse generator maximum DIDT is this 20 amps divided by 100 nanoseconds, 200 amps per microsecond. But we can estimate that current transformer and the Shunt, they are DIY versions, but they have same rise time as commercial Rogowski coil. So they are measuring accurately the rise time. So we can estimate that if they measure accurate rise time, it must upper cutoff frequency must be about 5 times higher than this 3.5 megahertz. So we can estimate that 5 times 3.5 megahertz, which is 17.5 megahertz. So we can estimate that DIY Shunt and DIY current transformer have at least 17.5 megahertz upper cutoff frequency. It could be higher, but at least this one. Okay, now the pulse and droop. So yellow line is the Shunt, and because of it is Shunt, it has no droop. Okay, we can see small droop, but it not because of sensor, it because of current pulse generator which has small droop. But we can assume that there is no droop at all. Okay, Shunt has no droop. And next one is Rogowski coil. It has about, we can measure it here. we 62 millimeters and Droop is maybe 56. Rogowski Droop is 62 minus 56 millimeter, and which is about 6 millimeter. 6 millimeter divided by 62 millimeter is about 10, 0.1, and we can estimate that di per I, its Droop, is proportional to T divided by tau, which is tau is T divided by di dt. So we get tau is 200 microseconds, which is this pulse length divided by 0.5, which is Droop, which is 2 milliseconds. And we know that cutoff frequency, lower cutoff frequency is 1 divided by 2p tau, which is 2p, which is about 80 hertz. What about current transformer? Same measurement. It is about, let's say it's about 50 now, 60. 62 minus 60 millimeters is 2 millimeter. And 2 divided by 62 is about 0.032, and we get tau, it's 200 microseconds divided by 0.032. 2.25 millisecond, and lower cutoff frequency is about 25 hertz. So we can now estimate that fast Shunt is about DC to 17.5 megahertz, and Rogowski is about 80 Hertz to 50 megahertz. Of course, this one is specified the manufacturer, and I could check this one too. I remember it's somewhere around 100-150 Hertz specified by manufacturer, but this is our rough result. And current transformer about 25 Hertz to 17.5 megahertz, something like that. Okay, study is done, and thanks for watching, and see you in the next video. Bye bye.